We've all been there. You're in the middle of a heavy mobile gaming session, and your phone starts burning up before glitching out. This graphic shows a new liquid epoxy system. By packing in microscopic silica particles in 2 different sizes, manufacturers can drastically increase the material's density. This structural packing physically prevents the microchips inside your phone from warping under intense heat. And this chart illustrates the enhanced wear resistance of a newly developed silver plating process. By embedding microscopic Teflon-like particles into silver without using toxic cyanide, electrical contacts and charger ports become significantly harder and last much longer under repetitive use. By reinforcing the material architecture at the molecular level, these upgrades ensure that our devices can withstand the thermal and mechanical pressures of daily life without failing. To build the next generation of hardware, researchers are turning to the strange math of quantum physics. This diagram illustrates a breakthrough called room temperature magnon coherence, a state where magnetic moments spontaneously align in the exact same direction, operating in perfect unison without needing extreme cold. When you combine that magnetic alignment with the concepts shown in this schematic, where separated qubits are linked by a 50-centimeter bath of entangled microwave photons, you get the baseline architecture for a completely secure quantum communication network. This image reveals the capability of a new achromatic neutron lens. The sub-20 micrometer resolution allows scientists to look deep inside thick, dense materials like commercial electric vehicle batteries to see exactly how they degrade over time. Mastering these microscopic interactions is the exact prerequisite for building reliable next-generation tools, like a stable quantum internet and safer electric vehicles. Zooming out, the persistent wave patterns driving heat domes across the US and Europe are compounding the brutal lived experience of Indian summers. The deadliest phase of these heat waves occurs after the sun goes down, driven by a phenomenon called nocturnal cooling failure. When overnight temperatures stay high, the human body never gets the chance to drop its core temperature and recover from the day's thermal stress. This overnight danger maps directly onto housing inequality. Thermally inefficient, dense urban housing absorbs heat all day and traps it inside, turning these tight neighborhoods into concrete ovens. To combat this, researchers are analyzing a recent street planting study out of subtropical Queensland, which offers a functional, data-backed blueprint for Indian smart city planning. The study found that placing trees directly in the center of the street and increasing the vertical layering of plants can drop the temperature pedestrians physically feel by up to 2 degrees Celsius. Urban street design and proper housing insulation act as vital public health infrastructure, directly saving lives as global temperatures climb. The threat extends to our water systems. In tidal rivers, when high coastal tides collide with elevated river discharge, the opposing forces severely amplify flood peaks, pushing massive volumes of water over the banks. We've seen these precise mechanics drive record flood levels in the Yangtze River, and they are the exact compounding forces threatening coastal Indian cities like Mumbai and Kerala during heavy monsoons. This map shows ocean acidity anomalies across the globe. The deep bands indicate how ocean acidification is leaving a permanent chemical receipt of our carbon emissions, shifting the water's pH far faster than the Earth's slow geological buffering can neutralize it. Right in the middle of that shifting chemistry, microscopic phytoplankton are wrapping themselves in structured chemical halos to trap nutrients, a mechanism that actively alters how carbon cycles through the marine environment. Watching vast Earth systems change is driving a documented global rise in climate anxiety, forcing us to rethink our footprint at every stage of life, prompting evaluations into the material and energy costs of traditional burials and cremations. Compiling these thousands of measurements into standardized databases does more than record the past. It creates the high-resolution baseline needed to predict future shifts and implement targeted local adaptations. Looking upward, our ability to understand the broader universe is accelerating. Space cargo costs are projected to drop 90% by 2040, unlocking massive, cost-effective launch capabilities for space agencies like ISRO. With those cheaper launches, we can deploy more heavy hardware. Already, instruments like the James Webb Space Telescope have resolved the mechanics of a supermassive black hole, capturing it feeding itself through a rotating disk and magnetically guided gas filaments. And despite discovering extreme cosmic violence, like stars being shredded by black holes, Einstein's theory of general relativity was validated yet again. Precise laser tracking of satellites proved his gravity models hold up to a 0.1% margin of error. Closer to home, the Curiosity rover cracked open a rock on Mars to find pure elemental sulfur crystals, a deposit that numerical models suggest was left behind by a massive ancient asteroid impact, melting the sulfur-rich crust. Observing these extreme cosmic forces and violent planetary histories is how we test the absolute limits of physics, proving exactly where our foundational theories hold strong under ultimate pressure. That understanding directly informs our next steps. We now have a global map of the moon's regolith thickness, showing an average dust layer of about 6 meters across the lunar highlands. Beneath that dust, lunar samples reveal the moon's deep interior contains structurally bound water, distinct from polar ice. This forces scientists to rethink the giant impact that formed the Earth-Moon system, as models must now explain how this water survived the collision. Extracting these resources and building on these models requires sustained human cooperation. Despite geopolitical tensions on the ground, Russian cosmonauts and NASA astronauts are still flying together and working side by side on the International Space Station. From the molecular packaging that keeps our technology stable, to the shade trees cooling our streets, and the water signatures found within the lunar crust, science provides the specific, material foundation for how we navigate our world.